All right, here's section 1.9. Um, Now, it turns out that every linear transformation, as long as it's from Rn to Rm, can be written as a matrix transformation of this form. So, uh, this is called the identity matrix, uh, where you have ones along the main diagonal. So for example, I2 would just be a 2 by 2 matrix with ones along the main diagonal there and zeros everywhere else. Here I3 has ones along that main diagonal and zeros everywhere else. I just realized we haven't actually defined what the main diagonal is, but hopefully you get the idea. So that has the property that that matrix times x just equals itself. It doesn't change things. And we did an example of that in the 1.8 notes that you can check out. So the two columns have special names. We call them E1 and E2. Now, you might notice that that's the same thing that you call uh, the vector 1, 0, you call it I hat in physics sometimes and in calculus 3 sometimes. And the vector 0, 1 is what you call j hat. Uh, and so this is just another name for I hat and j hat. The reason why we're using them, calling them E with subscripts, is because what if we have the I-27 identity matrix and we don't have enough letters, so we want to give them numbers instead. So you can check by multiplying if you want here that when you multiply this by 3, 4, you get 3, 4. Now let's by the way, this is a general advice for video lectures. It's a good idea to pause it as often as you can and try stuff on your own. Uh, you can make it take as long as it takes for you to really get it. You don't want to miss stuff just because it went by too fast. So you can always pause it and go back and repeat stuff and try doing things on your own. And that's a better way to learn than just trying to watch it straight through, maybe. So anyways, let's do this example here. So the first thing I want to do is, before we try to do t of x, I want to write x itself a different way. Well, we know that x is equal to the identity matrix times x, which you could write it as I times x like that, and you could also write it as 1, 0, 0, 1 times x1, x2, and you could think of that as just what happens when you multiply this out. You're going to do x1 times this first column, which is also known as E1. So that'll give you x1 times that E1 vector here. And then that result plus x2 times the E2 vector. That's just the definition of how to multiply a matrix by a vector. So this is another way of writing the vector x. Now, if we think of it this way, then we can say that x is a linear combination of these identity matrix columns, which it is. And we can use the definition of a linear transformation because we're assuming that this is linear, right? So it had better give you the same thing whether you do this linear transformation in the input or do the corresponding linear transformation in the codomain. So here's what I mean by that. T of x is the same thing as T of x1 times E1 plus x2 times E2. And because it's linear, that this must be equal to T of, I meant to say x1 times t of e1 plus x2 times t of e2. And that's doing the corresponding linear transformation with the output vectors as that we're doing with those input vectors. Now this, we could say, hey, I know what t of e1 and t of e2 is. I've got them right here. So it's going to be x1 times this vector 1, 2, 3, 4 plus x2 times this other vector like that. And then that, you notice, hey, this is a linear combination of these two vectors using x1 and x2 as weights. You could just write that as a matrix times a vector, where we take that column and make that be 1, 2, 3, 4, make that be the first column, and make the other column be 0, 1, 0, 1. And if you multiply that by the vector x1, x2, then that basically tells you what you need to do with x1 and x2 to get t of x. So just to summarize this here, t of x is equal to this matrix times x1 and x2. Because of the fact that it's linear, you can break down the linear combinations the same way in the input space or in the output space. I'm not sure if that made sense, but anyways, you could also write the formula here. I'll write it a slightly different way. T of x is just equal to t of e1, t of e2. I'm just rewriting these two vectors in a matrix and then multiply that by x. So this is a formula for that linear transformation. This is, by the way, what the 3 blue, 1 brown guy was talking about in his video, where he said you only need to know what happens with the I and j vectors to understand the rest of the linear transformation. That's true here too. You only need to know what happens with e1 and e2, because if you have any other vector, you can break it down as a linear combination of e1 and e2, and then the linearity property of the transformation means that you get this formula out for it. Oh man, I just listened to some of what I just recorded, and I heard all of those horrible popping sounds that somehow my microphone managed to generate, or my best guess is that it was the microphone cable that had other electronics interfering with it before it got to the little preamp thing. Anyways, I got the wrong kind of microphone, and then it turned out I had to get some other stuff to attach to it, and the whole setup doesn't work very well. I'm guessing that either my power cable or my modem was making some kind of electromagnetic something or other that was inducing a very small current in the microphone cable, and so I tried to fix it. Now that was more details than you care about. Anyways, hopefully it's better now. Let's look at this theorem. This is basically saying a more general version of what we just said, that if you have any Rn to Rm linear transformation, then there exists an m by n matrix A so that t of x equals a times x for all x in Rn. So, and specifically, here is that matrix. So this is saying that every linear transformation is a matrix transformation. Just like, in fact, we proved about R1 to R1 functions, those are equal to mx, and every linear transformation from R to R is equal to f of x equals mx for some number m. You can think of that number m as like a 1 by 1 matrix. But anyways, first thing we want to do is take x and break it down into a linear combination of the identity matrix columns here. That's what this is. And since t is linear, when you plug this transformation in, what you're going to get is the corresponding output linear transformation. x1 times t of e1 plus all the ones in the middle until you get to the last one, xn times t of en. And that linear combination of those output ones, you could just write that as a matrix times a vector. Remember, t of e1, these are all going to be vectors, so we can make them be the columns of a matrix. Like so. And that is all getting multiplied, or multiplying each of them by x1 through xn. That's just like multiplying the whole thing by the vector x. And there's a special name for this. This matrix here is called the standard matrix of a transformation. So this is a pretty important thing because every linear transformation has a standard matrix, and this is how you find it. So let's do some examples of finding standard matrices of transformations. So for this one, t from R2 to R2 reflects points across the x2 axis, which means this, if you take a point anywhere, the output is going to end up on the opposite side of the x2 axis, the same distance away. It should still have the same x2 coordinate because it just moved along the same height there, but the x1 coordinate should be the opposite of it. So the way we can get the standard transformation of this is by using this theorem and saying that t of x is going to be equal, the standard matrix is what we're looking for. The standard matrix is going to be t of e1 and t of e2. So if we just find those two vectors, we can just make them be the columns of this matrix. So here's a picture of e1. Let's see that here. Here's e2 at the point 0, 1. And let's think about what's going to happen to each of these. If you plug in e1 into this, you're going to end up at this point over here, still a distance of 1 away, but on the opposite side. So that would now be the point -1, 0. That is t of e1. And then t of e2, if it's getting reflected across the x-axis, it's going to be on the opposite side, but at the same distance away. But it's a distance away of 0 right now, so it's still going to be a distance away of 0. So t of e2 is just equal to e2. So here's what we can say. T of e1, this vector we're going to put here, the first column, is the vector -1, 0. T of e2 is the vector 0, 1. And that is the standard matrix right here. Pretty neat. So if you ever want to reflect some points across the x2 axis and you're not sure how, you can just multiply them by this matrix. Here is a tricky one. So for this one, to get an idea of what we're talking about, when we say r sub phi rotates points an angle of phi around the origin, and this works whether you're talking about radians or degrees or whatever. as long as you're consistent. Let's see what that looks like, because this is going to be a different transformation for different values of phi. So I found this GeoGebra applet thing that will help kind of picture what's going on. So if you rotate 0 degrees, then if you plug in the points in a triangle, they just stand where they are. But if you pick another angle, like, I don't know, a 90-degree rotation, let's say, a 90-degree rotation is going to take all of the points in R2, but we're only looking at one triangle, just so you can picture it, and rotate the points in that triangle 90 degrees around the origin. And if, well, they're calling it theta here, but if phi was something else, that would end up, your triangle would end up somewhere else, like over there or over there. And this is actually giving away the answer. This is what we're going to get, this cosine, sine, negative sine, cosine thing. And yeah, so it's going to be, and as you can see, it's a different result depending on what your values of theta are here. So, and I also want to point out that this animation shows you another useful thing, is it shows you what happens to the E1 and E2 vectors as they rotate however many degrees. So if E1 rotates 160 degrees, it ends up right here, this one here, and if E2 rotates 160 degrees, it ends up being right here. And that's what we're trying to find, is how to get t of E1 and t of E2 in terms of phi. So to get those, we're going to need to do some geometry. So here's E1, it's the point 1, 0, and I just want to draw a picture of what it looks like when that point gets rotated phi radians. It looks like I drew something that's, I don't know, maybe 50, 55 degrees, but it could be anything. A few things I want to point out. This is going to require a little trigonometry stuff that you might not remember very well. So you might have to watch this a couple times or do some drawing on your own to really make sure you get the trigonometry. One thing is this distance is going to be 1, because we're not changing the distance away from the origin of anything, we're just changing the angle. So that's a distance of 1. And then we can make a little right triangle here, like that. And if you have a radius 1, not radius 1, a hypotenuse 1 right triangle, we're kind of talking about points on the unit circle right now. I mean, we are talking about points on the unit circle. And the definition of sine and cosine is that sine of phi is defined to be the y-coordinate, or the height that this is above the x-axis. And cosine of phi is defined to be the x-coordinate this is, or the distance from the y-axis. So that means that this here we are. This y-coordinate here is sine of phi, and this x-coordinate here is cosine of phi, and that means that r sub phi of E1 is just cosine of phi and sine of phi. What's going on? There. Okay, now what about E2? This gets a little bit trickier. I'm going to pause it so I can draw a nice picture. So it's the same idea. We have a distance here of 1, because E1 starts a distance of 1 away from the origin, because of course it's the point 0, 1, and it gets rotated around, so you end up over here. And let's see, there's a few ways you can do the trigonometry to find the x and the y that you want here, the way I want to do it is by thinking of the standard position angle. Standard position meaning what is the angle you have to rotate from the x-axis. The way we did it here, it was okay because phi was already written as a standard position angle. But the standard position of the angle that you need to get to this point is actually 90 degrees plus phi, or pi over 2 plus phi. And so that means the x and the y coordinates of this are going to be cosine of pi over 2 plus phi and sine of pi over 2 plus phi. That's just the definition of cosine and sine. As long as your angle's in standard position, that works. And then there's some trig identities we need to use here. So cosine of pi over 2 plus an angle is equal to negative sine of phi, which kind of makes sense because it's like this horizontal thing I'm trying to picture here is the side opposite the angle phi. So when we're finding this x coordinate here, it should make sense that it's related to sine of that angle, because sine is usually about the opposite side of the triangle from the angle. And with the sine of pi over 2 plus phi, that's the y coordinate there. That should have to do with the side adjacent to phi, and the trig identity is that sine of pi over 2 plus phi is just equal to cosine of phi. So that means we can conclude that the r sub phi of E2 is equal to the x coordinate of it there is negative sine phi, and the y coordinate of it is cosine of phi. And so that means the standard matrix for it is going to be made up of these columns. Or in other words, if you wanted to say it a little differently, you could say that r sub phi of any vector x can be written as this matrix times x. And that is a pretty useful thing, especially if, I don't know, if you ever go into programming back-end stuff for video games or any kind of 3D graphics. You can imagine that you have to use this a lot because this is a pretty fast way to rotate things, to see where is a point going to end up after it rotates a certain amount. Also, I should say here, this gets used again in Chapter 5 later on when we talk about complex numbers. I don't know how much you know about complex numbers, but they describe rotation a lot of the time, and we're going to see how we can use matrices like this to sort of do a similar thing as complex number rotations. So it is a kind of fundamental sort of thing for a lot of applications. Now I'm going to stop this video here so that I don't fill up all the memory on my computer, and I'll record the second part of these 1.9 notes in another video. I will not see you then. I was going to say I'll see you then, but I won't see you because I can't see you right now, because you're not here, because I'm inside your computer. You can't even see me. This is weird. Okay, I'll see you in class next week.